DataMites family. In today's video, we'll be seeing about one of the transformation techniques called Box-Cox transformation. In Box-Cox transformation is a powerful transformation technique used to stabilize variance and make data more normally distributed. And this particular point being the most common for all the transformation technique. So the ultimate purpose is to stabilize the variance and make data more normally distributed. It is a flexible and widely used method for transforming data that is skewed or has no constant variance. Why use Box-Cox transformation? So I have listed out a bunch of reasons. One, let's say you have a skewed data, and by applying Box-Cox transformation, it can help to reduce the skewness in the data, so making it more symmetric. If it is more symmetric, easier to work with, so thereby it will increase the machine learning accuracy as well. And non-constant variance. Whenever there is non-constant variance, this Box-Cox transformation helps in stabilizing that variance, making it more consistent and easier to the model. Non-normal data. Whenever you have non-normal distribution of the data, it will help to convert it into a more normally distributed, not the exact, more likely into a normal distributed data. So this is to transform the normal data into normal distribution. So this is the formula. So if lambda is not equal to 0, then y to the power lambda minus 1 by lambda. If lambda is exactly equals to 0, then log y is applied. A logarithmic transformation is applied, where y is the original data and lambda is a parameter that determines the transformation. Purpose, as we have discussed, one, to stabilize the variance, improve normality, enhance interpretability. When to use it? When we have a skewed data or it has a lot of outliers. Second situation is when assumption of normality is critical for statistical methods. Example in case of linear regression. And data exhibiting exponential growth pattern. We go ahead with Box-Cox transformation. Effect of transformation. Normalization and for stabilizing the variance. And application is in statistical analysis, we use it mainly in regression analysis, ANOVA and other tests that assume normally distributed errors. Process improvement, valuable in Lean Six Sigma projects for analyzing process data and improving the efficiency. What are the limitations? Limitations being interpretation challenges. The transform data may be harder to interpret, especially if lambda is not close to 1. Data restriction requires all input data to be positive, negative, or 0 values. So the whole and sole purpose, let's say I have a positive value, it is fine. If let's say it is a negative or a 0 value, then we need to adjust it before transformation. So this particular Box-Cox transformation, the input data, it expects it to be positive. Choosing lambda. The optimal value of lambda can be determined by using maximum likelihood estimation. So this is the technique to find out the optimal value of lambda, and lambda is the one which is the core reason for applying this particular formula, often implemented in statistical softwares packages. Example, sci-fi.stats.boxcox. This is the technique used in Python. If lambda is equals to 1, let's say, means the data is already normally distributed and transformation may not be necessary. So check out for the lambda values. So let's see the practical implementation part. So here again, I would like to highlight the point. It is applicable to non-negative data. Even if you are getting negative or 0, you have to convert it. So this transformation involves raising the data to a power. What is that power here? Lambda, which we'll be finding out with maximum likelihood estimation. So I'm taking a column from loan amount CSV, column named as loan amount term. So from sci-fi.stats, I have imported Box-Cox. In this Box-Cox, I'm fitting my column, loan amount term. So let me show you the data. So this is the data, loan amount tenure. So here you can see the loan amount tenure. Let's proceed with our transformation. So by fitting this particular loan amount term column into the Box-Cox, we can see we have transformed the data. This particular output, I'll be storing it in two variables or two identifiers, the transformed data lambda value. So if I go ahead and print the transformed data, this is our transformed data. So each and every data point, as the formula which I have shown you, the formula got applied on each and every data point, and lambda at the back end got calculated, and this is our transformed data. And this is our lambda value. If lambda value is 1, again, it means already it is normally distributed. So here, the lambda value is 3, which is a good thing. It is close to 1. So this is the Box-Cox transformation. If you try to plot the graph, you'll be getting a graph which is something very likely or very close to a normal distributed graph. So thank you for watching the video.